Hello students, today we will discuss about chapter number 5th as we are aware about some of the formulas of chapter number 4th. Same we will go for the chapter number 5th. That initial portion of chapter number 5th is called as the introduction of a magnetic field, properties of magnetic field lines. Those field lines are equivalent to electric field lines, but there are some of the minor changes. As we have discussed some of the properties of magnetic field lines in chapter number 4th, so there is no need to just repeat it over here again and again. So we will start straightforward to the another expressional part of chapter number 5th. As you are aware that in the past I have also told you that chapter number 5th and chapter number 4th are correlated with the chapter number 1 and 2 of your 12th science. It is called as static electricity and electric potential. If I want to compare this chapter with the 11th science, so there are some of the opportunity I have received to just correlate is that chapter number 8 is called as a gravity. So you can correlate gravity, you can correlate with the chapter number 1 and 2, and you can also correlate with the chapter number 4th and 5th. So whenever you are opting for JEE or NEET, go for the sequential part so you can have a better idea, only replacement of some of the constants and you can reach to their formulas. As I am also repeating this theory because in chapter number 4th we have also discussed about one of the expressional part. It is called as our circular ring which is carrying current. So gradually we are moving towards that formula. But first of all I have just shown you that one bar magnet and it is containing that radius that is called as, let's say I'm just putting its radius is called as small a, as already have mentioned over here. That axis, let's say perpendicular axis to that point P where I want to find it out my magnetic field is somehow r distance away. That small segment dx, let's say this is the small segment dx. This small segment dx is a small x distance away from my perpendicular axis. So that remaining portion from the dx segment to that magnetic field at this point is called as a r minus x. So my task over here is that I want to find it out my magnetic field because of this dx segment which is r minus x distance away and located at point P. At this point I want to find it out my magnetic field. So this is my task. So first of all I want to just mention it out that I want to find it out magnetic field at point P. Let's say I'm just mentioning that dx small segment is, let's say, r minus x distance away from it. Another point I want to mention over here is that a radius of my solenoid is equals to small a, and let's say I'm mentioning that dx segment is located at small x distance away from perpendicular axis. So these are the mentioned part I have mentioned as per my theorems. So these are the formulas. One more important and interesting fact is that if you observe this figure, I have mentioned that that perpendicular line which is passing from my solenoid's midpoint is that it is making it equal distances. It is called as L and L because that you can see that 12 it will give you that reminder of a magnetic dipole moment, and that is why I want to derive this expression in the terms of magnetic dipole moment. So I can just also add one more thing that length of this solenoid is equals to 12. So these are the data I have mentioned over here. One more good thing I want to recall over here is that chapter number 4's equation that is called as my magnetic field of current carrying loop. If you recall this formula, it is called as a B is equals to mu 0 upon 2 Ia square and over here x square plus r square raised to 3 by 2. Let's say I'm just mentioning that equation number 1, and this is the equation. If you recall this one, this is called as r square. You recall this formula, if you recall this theorem or figure, you can see that I have placed over here that small r distance. In that theorem we have just mentioned this one as x. Here I have radius is a small a. I have mentioned over here it was in the that theorem is called as a capital R. So what I am doing is that instead of this x distance away, what I will do is that, let's say I'm mentioning that a point A, this is point B, so my from A to P distance, which is called as r dash, as far Pythagoras is concerned, so this distance from here to here is called as r minus x. You can see, and that is called as my adjacent side. My opposite side contains a small a, so my Pythagoras is called as r dash, which is called as a square plus r minus x is a square, and it's a square root. So over here I will mention those data over here, and my formula will be ready for me. Instead of right now I have small a over here because it was that formula which is I had in the past. At that time we were replacing that capital R. So here I'm in a hurry, I have placed, okay, it is r square. So in the hurry I have placed small a square because of this one, because we will place r equals to a. So this is the same formula we will place over here. I'm mentioning that r equals to a. If you have placed a, that is also okay, because in the next segment we are also supposed to put that same formula. So same equation we are putting over here, and my equation will be ready from the previous formula which I have placed. By some mistake I have placed small a. Same formula I will place over here. Here I have n number of turns on the loop. So I am mentioning that n number of turns are there. So my magnetic field dB is equals to mu 0 n number of turns Ia square divided by 2. Instead of capital R and X, I will place that R minus X square plus A square raised to 3 by 2, and this is for the dx segment. Look at over here, I have this hypotenuse, so instead of x and r, I have placed r minus x square because it was my hypotenuse. Capital R square is replaced by small a because it is my radius. So all those data is mentioned over here. So my equations are ready. You can see also one more thing, that my limit I want to place. Let's say this is my origin O. So from the right hand side it is plus L, and from the left hand side it is called as a minus L. So my equation will be like this. So I can have dB is equals to mu 0 Nia square twice times of r minus x square plus a square 3 by 2 integration dx minus L limit and plus L limit. I am mentioning over here x equals to lies between plus L and minus L. So I can also take integration over here, and you are aware that integration of dx is only x. One more thing I will mention over here, that you can see that my r minus x or r, total r, is somehow larger than a small a, which is our radius, and also larger than a small x, and also larger than a small l. So I will mention over here, so it will be quite easy for me to neglect those facts of denominator. So I want to just reduce this thing, that is why I am mentioning it. R is a very greater than L, and R is very greater than X, and R is very greater than A. So you can just neglect all those things, that is R is only left part. So I can have r minus x square plus a square raised to 3 by 2 will be only giving me r cube. So I am putting down those data in this expression. So these are my manipulative work to reduce my denominator. So now my formula after such type of data placing or data placement will be b is equals to mu 0 Nia square r cube, because I have just neglected this part, 2 is left. Integration dx is x, upper limit is plus L and lower limit is minus L. So you are aware that upper limit minus lower limit, so b is equals to mu 0 Nia square divided by 2r cube L minus minus L. So my equation will be b is equals to mu 0 Ni a square ln minus ln plus L, that is called as a 2L, and divided by 2r cube. I am perfectly okay with this formula, but I don't want this formula, because that I want that this equation or this formula or my solenoid will behave as a magnetic dipole moment, or show this formula in the terms of magnetic dipole moment. So this formula is perfectly okay. I am, let's say, just giving that equation number second one, but I want this formula in the terms of magnetic dipole moment. So there are some of the manipulative work I have to follow. So first of all, what I am doing is that I want that this equation in the terms of magnetic dipole moment. So I am putting that equation of magnetic dipole moment. So this is my magnetic dipole moment, is represented by small m, and that is called as a mania. Yes, in classroom we have sometimes laughed because of that Mia. People are right now m equals to Nia, n equals to number of turns. Now let's say I'm just giving that equation number a. In this expression, or some of the properties of this formula I will place in this above expression. So first of all, what I am doing is that you are aware about that number of turns per unit length. I have my length is 2L and number of turns are n, so I can have n is equals to small n into 2L. You can compare simultaneously. You can see that small n is there and 2L is there. Small n 2L is there, which will be replaced by capital N. Apart with that, our area of this solenoid. So my area of a solenoid is equals to A is equals to pi a square. Let's say this is equation number C. You can see that I have a square available, pi is missing, so I will just multiply expression number 2 with pi in numerator and denominator, so my task will be comfortably completed. So what I am doing is that equation number 2 is now multiplied and divided by pi. So my equation which I have placed over here is that a mu 0 will be b is equals to mu 0 ni a square 2l pi and divided by 2 pi r cube. And now I am arranging this all those terms together which may solve my task. So first of all, what I will do is that n and 2l placing together. So I have mu 0 n and 2l together, then pi a square together, I is left as it is, 2 pi r cube. So my equation number a b c, equation number a is called as a nia. Okay, uh, capital N equals to n2l. Yes, it is called as a mu 0 n, mu 0 n. Then after that this is solved. Pi a square is called as a capital A, so nia, and my formula is called as a 2 pi r cube. And from small a, I can say nia is called as a small m, mu 0 m 2 pi r cube. So this is the equation I am comfortable with. Apart with that, you can multiply by 2 because we are habitual to place 4 pi in the denominator. Again, this formula is also true, so this is 2m 4 pi r cube. This is the equation of solenoid. It's a magnetic field and magnetic dipole moment. So you can remember that solenoid can also behave as a magnetic dipole moment. So this is the proof of it. So in the school exams or so many exams, people are asking this theorem for the 2 or 3 marks. So this is the formula you can remember or recall, that is called as a magnetic field equals to B equals to mu 0 m upon 2 pi r cube, or B is equals to mu 0 2 m upon 4 pi r cube. This is called as the equation of solenoid. It's a relationship with the magnetic field. As far you will also see that one more comparison, instead of B, if you will place E as well, then our formula will also give me the reminder of chapter number 1, electric field and electric dipole moments relationship. This is also look like same. At that time, whenever our electric dipole moment was there, the denominator is called as a cube of it. Same is the course when I have magnetic field and magnetic dipole moment, my denominator is called as a cube. So frequently, whenever you will prove some of the equation, always compare with the chapter number 1. This is the primitive advice. Whenever you will go for the revision, automatically if you will compare, you will be in a position to give that answer of each and every question or revision of your chapter number 1. Okay.